Greetings everyone. So till now we have studied about relations, types of relations, equivalence classes, then function, types of functions, bijective functions, and I hope that is completely clear to you. Now we will move forward to composition of functions. So let us see what it is. Suppose we have three sets A, B and C. Okay, and suppose there are two mappings. One is from A to B and the function is denoted by F. Another one is from B to C and function is denoted by G. These are two different functions, suppose. So for function F, your domain is A and codomain is B. For function G, your domain is B and codomain is C, right? So G is mapped from B to C, right? F is mapped from A to B, right? Now suppose we have to find a function that is mapped from A to C directly. This function is now called composition of two functions. What two functions? F and G. Now if we have to find a mapping that goes directly from A to C denoted by G of F. This G of F function is called composition of two functions F and G. Now let us see. Suppose there is an element x. So when this will be treated with the function f, what will we get in the image? F of x. Alright. I hope this is clear to you from the previous topics. Now for the function g, this b is the domain, right? So now when this element is treated with the function g, what will we get in the codomain? Means what will we get as a result? G of fx, right? So ultimately when we are treating g when we are treating x in g of f, what are we going to get? This is equal to g of f of x. This is how you denote. Now we will see how it works. Suppose we have two functions. F of x is given by x plus 5 and g of x is given by x square, and we are asked to find g of f. Alright, so we will apply this, right? For g, your domain will be f of x. Alright, so what is f of x? F of x is x plus 5. Alright, so what do you get? You have to treat g on x plus 5 now. Right, f of x is what? X plus 5 only. Now you see what your g function is doing. For x, it is giving you the square of x, right? So for x plus 5, what will your function g give? It will give you x plus 5 whole square, right? So this is g of f. Now when you do the composition of fx and gx, and you have to find g of f, you will get x plus 5 whole square. So this is how it works, how g of f works. Now keep one thing in mind. Suppose we were to find f of g. Suppose. Then what would have happened? See, when we have to find f of g, the mapping will go reverse. All the mappings will go reverse. Now what would happen? Your domain for g would be c and your codomain would be b. And the domain for f would be b and the codomain would be x. Right? So when we are going to find f of g, it will give us f of gx. And later we will see that f of g and g of f are not equal. See, f of this is not commutative in nature. We will find this with the example that f of g is not equal to g of f. We have reversed. When we have to go from g of f to f of g, we have completely reversed our mapping. Alright, so let us quickly see this with an example. Here we have two functions f and g. F is a mapping from r to r and f is given by cos x. G is a mapping from r to r and g is given by 3x square. Now if you have to find g of f, so let us see, your g of f is going to be g applied to function fx. Alright, so what is your fx? Fx is your cos x, right? Now when you have to apply g function on cos x, what is it going to give you? 3 of x square, right? So 3 into, when your domain is x, right? When g is treated on x, what it is giving? It is giving 3x square, right? So when g is treated on cos x, what will it give? It will give you cos x whole square, right? So this is what you get, 3 cos square x. This is your g of f. Now let us find f of g here. For f of g, what you have to do? You have to apply function on the domain gx, right? So what is your gx? Gx is your 3x square, right? Now what is the function f doing? Function f, for x, it's giving you cosine of x, right? So for 3x square, what the function is going to do? It's going to give you cosine of 3x square, right? So this is your f of g, this is your g of f. Now you can clearly see this, that composition of two functions is not commutative in nature. F of g is not equal to g of f. Alright, so this is about compositions of function. Let us once again look at this diagram in order to find the identity of f of g and g of f. See, identity of function is what? Suppose this is a mapping, right? And if x you start from x and reach to x only, means if your f of x is x, then x is the identity, right? X is the identity of this function, because you started from x, you applied the function on this element, and again you got what? X only. So x is now the identity of this element, of this function. Similarly here also, for g of f, you start from what? You start from x only, then x is treated with the function f, then f is treated with the function g, f of x, and again if you are able to get x, right? So this x will now be the identity of this function, which is denoted by ix. Similarly, if we are to talk about f of g, right? F of g will start from y, will be treated with this function, and if again you are able to get y only, then this y is called iy, identity of the function, right? So keep these two things in mind, because these two results are going to help you in a lot of numericals, that ix is x only, iy is y only. Alright, so these are the identities of the mapping, means identity of the composition of the two functions. Alright. Let's look at this question from NCERT. There's a function f, which is a 1-1 onto function, and mapping is done like this. And they've asked you to show that there exists a function g like this, such that g of f and f of g are identity functions. Identity function means if g of s is operated on any alpha, it will give you alpha only. These kinds of functions are known as identity function. Similarly, if f of g is operated on any beta, if it gives you beta only, then f of g is also an identity function. So this is what we have to prove, right? So they have asked you to show that there exists a function like this. So let us simply assume, it is very easy to verify. Let us simply assume that there exists a function g, and let us apply g of f. So see, f has how many elements? 3 elements. So let us individually apply it for all. See, f of 1 is what? F of 1 is a. F of 1 is a, right? So g will be applied on what? G of f of x, right? So what it is? It is g of a, g of 1, right? G of 1 is what? Sorry. Fx is a. G of a is what? 1 only, right? So what did you get? G of f of 1 is 1 only. Let us take it for 2 also. Similarly, g of f for 2 will also give you, means g of what? G of b. What is g of b? Is 2. Similarly, g of f of 3 is also, g of c. What is g of c? G of C is 3. Similarly 3. So what did you find? G of alpha is alpha only. So what did you get? G of f is your identity function. Similarly, you can prove it for f of g also. You will get f of g is also a identity function. F of g is also identity function. You can prove, you can verify it on your own. So this was about identity function. Invertible function or inverse of a function. See, suppose there is a mapping like this. And the function is f. Now, if we are able to draw a mapping from the codomain to the domain, means in reverse order. Suppose if we are able to draw a mapping from here to here and give it a name, supposedly G. Now, if this mapping is also a function, means every element is mapped and is mapped to a unique element in this set, then G is also a function, right? Now, if f is a function and we are able to draw a mapping in reverse order, then this function will be the inverse of f. Means f is an invertible function and inverse of f is g. Now let us see what mathematical approach is followed. A function f mapped from x to y is invertible if there exists a function g from y to x such that g of f is identity function and f of g is also identity function. Alright, so read it once again and let us understand this with an example. See, suppose there is a function fx is equal to y. Now in order to prove that fx is invertible, you have to find something like g of y is equal to x. And if this function g exists for all the elements of the domain, then we will say that f is an invertible function. But this is not complete yet. You have two more properties to satisfy. G of f should be identity function and f of g should also be identity function. So first of all, you will have to find a g of y, and then followed by g of f is equal to ix and f of g is equal to ix. Then overall you can say that our f was an invertible function and the inverse of f was g of y. Alright. Now let us look at this example. There is a function which is mapped from a set of natural number to y, and the function is given by 4x plus 3. Now what is y? Y is a set that contains all the y's belonging to natural numbers such that y is equal to 4x plus 3. Now we have to find whether fx is an invertible function or not, and if fx is an invertible function, what is the inverse of fx, right? What is the inverse of the function? Now see, first thing that we have to do is, for fx is equal to y, we have to find a function g of y is equal to x. And if this satisfies for all the elements, g of y is equal to x, then we will say that our function is invertible. And not only this, we have to find whether g of f is equal to ix, means identity, if g of f is an identity function or not, and similarly if f of g is an identity function or not. So we have to do these three things, and if we find all these three properties satisfying, then we will say that our fx is invertible function, means our fx 4x plus 3 can be inverted. And what will be the inverse? This g of y. Whatever function we find here will be the inverse of your fx, and this will be in terms of y. So let us just begin. See, f of x is equal to 4x plus 3 is equal to y, right? So 4x plus 3 is equal to y. Then we have to find a function of y, function in the terms of y. 4 of x is what? Similarly, what you have done in onto function, the same procedure you have to follow here. In order to prove if a function is onto, what you used to do? You used to convert f of x into g of y, right? Same thing we have to do here. Now x is what? No, it's actually y minus 3 and then y minus 3 upon 4. Alright, so you got x is equal to this, and you can see that for y, what is y? Y is a natural number only. You will find this satisfying. Alright, so you got that g of y is equal to x. What is g of y? Means y minus 3 upon 4 is equal to x. Now one condition is satisfied. Alright, okay, So let us find g of f now, g of f of x now. What is it? G operated on the function fx, right? So what is this? What is the function f here? Function f is 4x plus 3, right? Now what is the function g? G of y is y minus 3 upon 4. So in the place of y, what are you going to put? 4x minus 3. Alright. So what will you get? 4x plus 3 actually. 4x plus 3 in the place of y minus 3 upon 4. Alright. Right? So what is the g of f of x? 330, 4 cancel is x only. So what did you get? G of f of x is x only. This means it is an identity function only. Right? So another property is also, condition is also satisfied. Similarly, if you check for f of g, suppose f of g is what? F of g of y is what? F operated on g of x of g of y, right? So what is it? Function, what is g of y? Y minus 3 by 4, yes? Right? So again apply function f. So what is this? 4 upon y minus 3 of 4. Here is it? It will be plus also. What are you going to get here? Y plus 3 minus 3, right? Is it? It's y only. Similarly, see. Here also what you got? F of g of y is y only, right? So f of g of y is also an identity function. Is also an identity function. So let us see is as a whole. First of all, we were able to find a g of y. Then we were also find to prove that g of f of x is identity function. F of g of y is also identity function. So overall, what we can conclude, that our function is invertible function. Alright, and the inverse of the function is g of y, means this is the inverse of the function and our function is invertible. So this is how you solve. First, for f of x you will find a g of y, right? And you have to look that it satisfies for all the elements of your domain. Then after this you have to prove that g of f is also an identity function, f of g is also an identity function. Then overall your function is invertible. Now look at this. If a function is invertible, it must be 1 1 onto, means bijective, and conversely, means if a function is invertible, it has to be 1 1 onto, and if a function is 1 1 onto, then it must be invertible. Look, let us see how. Suppose there is a mapping, right, and it goes like this. 1 is 2 is mapped to, and 3 is also mapped to. See, it's not, now you see this is a many one function, many one and into, right? Now let us try to inverse it. So if you do a mapping from this, first of all it's not a function, because if you are to map inversely, c is not mapped, so it will not be a function. So this was the case of many one into. Similarly, you can verify this for all other mapping except 1 1 onto. Means suppose it is 1 2 3 and A B C. Suppose it's like this. Suppose it's like this. 3 is also mapped to B. Now you see, what is this? This is many one onto, right? Many one also and onto. But when you are to find inverse of this function, suppose it goes reverse way. Now you see, again this is not a function in the reverse way. Why? Because you see, B, for B you have 2 also, for B you have 3 also, like this. Suppose here is AB is 1 2 3. A is mapped to 1, b is mapped to 2 also, 3 also. Now again this is not a function because b does not have unique image in the codomain, right? So this can also not be a function. So whenever you have to prove that a function is invertible, first of all it must be a 1 1 function, 1 1 onto function. See how? Suppose ab 1 2. Now 1 is mapped. See, this is a 1 1 function, right? Now if you reverse it, what will you get? 1 is mapped to a, 2 is mapped to b. Again this is a 1 1 function. In this case only function is invertible. Otherwise if you inverse the function in this case or this case or any other case, first of all it will not become a function only. The inverse you will talk about it later. First of all it will not even become a function. Okay, so I hope you understand why this is true. A function is invertible only if it is 1 1 onto, and if a function is 1 1 onto, then it is invertible. The function is 1 1 onto, you can easily inverse this function. There is a set S and there is a function mapped from S to S. Then you are asked to find whether f is invertible, and you have to, if f is invertible, you have to find the inverse of f. So for a function to be invertible, the very condition is that the function must be 1 1 onto, right? So let us check if it is 1 1 onto. You see, it is mapped from S to S. So 1 2 3, 1 2 3. 1 is mapped to 3. 3 is mapped to 2. No. Yes. Now 2 is mapped to 1. Right? Clearly it's a 1 1 function. Since f is a 1 1 function, f is invertible, right? So let us find the inverse. It's very easy. Look, these type of questions can be easily done when you draw the diagram, means when you do the mapping, it can be very easily done. Now if you have to find f inverse, means reverse. Let us see. Now you see, 1 is mapped to what? If you have to see inverse, 1 is mapped to 2, right? 2 is mapped to 3 and 3 is mapped to 1. So easily this is the inverse of the function. What you did, first you found whether the function is 1 1 onto or not. Clearly it's a 1 1 onto function, 1 1 onto, and then you reverse the function and found the inverse of the function. Alright, so this is very easy. Let us take another example. So let us check if it is 1 1 onto function or not. Simply it is mapped from S to S, 1 2 3, 1 2 3. 1 is mapped to 2, 2 is mapped to 1, 3 is also mapped to 1. First of all, this is not a bijective function because this is a many one function. It's not a 1 1. If it's not 1 1 or injective, it's not a bijective function. So first of all, this function is not invertible, so there does not come a need to find its inverse. So f is, since f is not bijective, f is not invertible. That's all for composition of function and inverse of function. I hope you have understood it, and if you have any doubts, so you are free to reach out to me. Thank you.